Second MYCO University. Glad to see you all here this afternoon. I think everybody knows who I am, but I'm Steve Fields, Curator of Natural History here. So this is number 2 in the series of, just talking about some general fundamental concepts in ecology and biology. And as we go on, we'll get a little deeper into some concepts that probably seem to have a little more direct bearing on what we do here at the museum. But I always feel like it's good to have a basic knowledge of concepts when you're going to be doing any kind of natural history or biology interpretation. And it doesn't get much more fundamental than matter and energy. But the way that matter and energy go through living systems, and remember last time we talked about living systems being basically our definition of what is life, because it's hard to define life. If I ask you what is life, what are you going to tell me? Because you can define it on levels other than that of biology. As I said, metaphysical, physical, spiritual, whatever. So we said living systems have certain traits and characteristics and are organized in certain ways. And also the way that matter and energy move through them is somewhat different. So, this is going all the way back for me to elementary school. And, when a teacher would ask you, what is matter? And we always had that same canned definition that when I look back on it was wrong. But, we would just spout it out like we were, reciting the Pledge of Allegiance. Matter is anything that has weight and takes up space. That sound familiar? Well, you say, well, what's the difference between that, which you're saying is wrong, and this statement, which is correct? Matter occupies or has mass and occupies space, the material of which things are made. Fundamentally, one is weight, one says mass. Those are not the same things. Not the same things at all. Because weight and mass don't account for the same thing. Best example I can think of is that, you can say, what you weigh here on Earth, and since you're not likely to leave this planet, that's not a big deal. You're subject to the same gravitational force, and that's what's different. Weight takes into the account the force of gravity exerted on an object of mass. So if I travel to the moon, which is 16% of the mass of the Earth, then I'm only going to weigh 16% of what I weigh on Earth, because there's much less gravity. So if I weighed 100 pounds on Earth, I'm only going to weigh 16 pounds on the moon, because the force of gravity is taken into account. However, if my mass is 45 kilograms on Earth, then my mass is still going to be 45 kilograms on the moon, because weight doesn't come into it. So mass is literally the amount of matter in a particular body. All right? And so that's why mass is a better definition than weight. And, in school we learn about, and this is something I know we talk about to kids here, we talk about hypotheses and theories and, the difference between the two, and ultimately what are called laws in the natural world. So there aren't too many laws out there because, they're pretty much not going to be refuted under normal circumstances. So talk about this law of conservation of matter. What does that mean? It says that matter is not created, it's not destroyed. It can be recycled, it can be moved around, it can be transformed, it can be combined with other matter, but no matter what you do with that matter, the amount in the universe is always going to be the same. So if I, go over to the trash can here, or somebody in Virginia's probably done too good of a job of recycling here, but let's say I've got this piece of paper here, and, if I were to put it on the scales, it would tell me there's a certain amount of mass here, right? And, well, all right, I don't want this anymore, so we say, we're going to throw it away. What does that mean? Like I said, there is no away. At best, you're moving it from one place to another. Okay, well then I'm going to recycle it. Well, that's going to get taken, and literally, like the definition says, you're going to take at least part of it and put it back into something else. Or, okay, well then I'll just burn it. That'll certainly get rid of it. All that'll be left is a little bit of ash. Well, that's true, but a lot of that is gone up into the atmosphere as small particulates. And were it possible to regain all of those particulates and bring them back down to Earth and put all that back together, you'd see that it's exactly the same. Because you can't create matter, you can't destroy matter. But you can move it around. Now, it's always neat to see the law of conservation of matter at work. It's not just some abstract law that's out there. So think again, going back to elementary school and hopefully a few other times throughout school that you learned the process called photosynthesis, which is how plants manufacture the food that they need, right? Utilizing sunlight and some basic elements. So the formula for photosynthesis is this. It says that carbon dioxide and water, and there's also some energy required, are combined to form this molecule, which is glucose, basic sugar, and in the process, oxygen is given off as a byproduct, okay? That should be somewhat familiar to you. All right, but my question is this. Does that equation satisfy the law of conservation of matter? In other words, we're told that you can't create matter, you can't destroy matter, but you can mix it up. Well, I'm taking this and mixing it up, and I'm getting this, so that means the amount of matter over here has to be exactly the same amount as the matter over here. Do you remember doing something in school called balancing equations, especially in chemistry or probably physical science? We did it for weeks in my 9th grade physical science class. It was actually kind of fun. In other words, making all the molecules and atoms balance over here by adding numbers. But through it all, I don't think my teacher ever once said why we were doing it. Why were we doing it? To satisfy the law of conservation of matter. So all right, let's answer the question. Does the law fit here, or does this equation conform to the law? So let's look at the components here. We'll see these are molecules, but the basic atoms, there's carbon, oxygen, and hydrogen, right? You see C's, H, and O's. How many C's are on that side of the equation? One. How many C's are on this side of the equation?
6.
6. Okay, so we got to make some changes to make it fit. So if there's 6 on the right side, then there's also got to be 6 on the left side, right? It's hard to draw that thing. All right. So now there's 6 carbons over here, there's 6 carbons over here. How many oxygens are on the left side? 1, 2, 3. Okay. How many are over here? 8. What about hydrogens? 2 on that side, 12 on that side. All right. We're not going to spend this time, trying to figure all this out, because the answer is that you actually have to put a 6 here, and you have to put a 6 here. And if you then add up the C's, the H's, and the O's, they are now balanced. So what the equation should tell you is that it takes 6 molecules of carbon dioxide plus 6 molecules of water to create 1 molecule of glucose, the food that the food source the plant's trying to get, and then you're giving off 6 oxygens as a byproduct. Now that equation conforms to the law of conservation of matter, and that's the way it happens in plants. All right, so that's matter. What about energy? What is energy? That's another one of those terms that's a little bit difficult to define. I think we know what it is, and it can be defined in a lot of different ways. But basically, it's simply the capacity to do work. Because we've all felt that before. I don't feel like working. Why? I don't have any energy. We say it metaphorically, but there's some truth to that. But remember, we're talking about living systems here. So what is work in living systems? Well, things like growth, metabolism, movement, reproduction. Do those things sound familiar at all? We learned about those last time. Those are characteristics of living systems. And every one of them take energy. So life requires energy. So metabolism, processing food, raising young, obviously takes a lot of energy. So just like matter, we've got some laws that govern the movement of energy in the universe. And there's actually two of them. The first one's called the first law of thermodynamics, and it looks very much like the one for matter. Energy is conserved. It's neither created nor destroyed. You can change it from one form to another, but in every reaction, the amount of energy is going to remain constant. So another way of saying that is the quantity or the amount of energy is unchanged in the universe. But there's a second law that deals with energy. Yes, you can change energy from one form to another, but when you do, you are going to degrade some of that energy into a less useful form. It's not going away, it's not destroyed. The first law says you can't do that. But it degrades it into a form that cannot then be used for work. So heat is usually the result. Infrared radiation heat is given off in these reactions. So this is energy, but it can't be put to work, back to work for any kind of work in living systems. And sometimes this disorder that arises is called entropy. Just like right now, there are agents of entropy all around us, just waiting for us to die. And as soon as we do, they're going to start to work on us, turning us back and recycling us back into the universe again. Okay? So another way of saying this law is that the quality of the energy is changed. So the first law, the quantity is not changed. The second law, the quality is changed when you change from one form to another. So let's give an example that doesn't even deal necessarily with living systems. Again, we've all heard this definition for something called potential energy. That's stored energy, such as the chemical energy in the gas tank of your car. Gasoline serves as chemical energy. Kinetic energy, energy of motion. And so we use that gasoline as a source of energy, and we convert that potential energy in the gas to the kinetic energy of movement in our cars. And in the process, the engine gets hot, and it gives off heat because there's an energy conversion going on. So we're changing energy, potential energy of the gas to kinetic energy of motion in a car. That's the first law. The second law says, if you do that, you're going to have some resulting loss from the system that can't be reused. The best way to think about that is this. The amount of energy hasn't changed here, but what you cannot do is take a pipe and connect it to the exhaust pipe of the car and run it back to the gasoline tank of your car, right? That's not going to do you any good as far as getting any movement or energy out of that.
Unfortunately.
Unfortunately, especially these days. If they ever figure that out, we'll be in great shape. So there's always a loss when you convert that energy. So where does this energy come from ultimately? Well, if you live on this planet, 99% of all living systems on this planet ultimately depend on the sun as that source of energy. I say 99%, so that means there's something that actually is a little bit different. And this is a relatively new concept in the natural sciences, and we'll talk about that at the end. But the flow of energy through almost all living systems can be traced back to the sun. And the most basic way is something, again, you've known since early in your childhood education, something we would basically call a food chain. Because you've got these plants, these organisms called producers, they can conduct that photosynthesis, and they can change the energy of the sun using that matter of carbon and oxygen and hydrogen, and use the energy to drive that process of photosynthesis, and then they can make their own food. Well, not all organisms on Earth can do that. They're not all producers. So if you're not a producer, If you're not converting the sun's energy, then you got to be getting it by consuming other organisms that do, or other organisms that consume other organisms that do, or on down the line. So you're either a producer or you're some kind of consumer. We'll talk about those specific niches when we get into the discussion of biological communities later on in the series. So, once again though, the movement of matter and energy have different fates, even in a food chain. So this is a very basic food chain where I've got a plant, a caterpillar, a small bird, such as it kind of looks like a chickadee, except it's purple. It's a clip art, not a true picture. And then a bird-eating hawk, such as a sharp-shinned hawk or something like that. So, remember the first law of conservation, or the law of conservation of matter, starting with the amount of matter or biomass that's in plants, gets passed from one organism to another with the ingestion. So the matter's literally coming this way. There's an old saying, you are what you eat. We're familiar with that. And on a biological level, it's very true. All right. So not just eat, but ingest. So Steve got this cola beverage over here, and as he ingests it, those molecules that form that cola beverage will be rearranged and become a part of him. So we're turning cola into Steve, essentially, right? Makes you happy too, right?
Science.
Science, that's right.
Oh, he's bubbly.
So, this is not just a one-way street though. Remember, we said that you can recycle energy, or you can recycle matter, and that's exactly what happens, because ultimately every single one of these links in the chain is going to experience death. And when they do, there are agents out there, those agents of entropy I was telling you about, decomposers, bacteria and fungi, that recycle the nutrients of that matter in the bodies, usually down into the soil, into the most basic of nutrients, then get recouped again up through the plant roots. So that's literally your cycle of life, and matter is recycled in this way through the food chain. Energy, however, is different. Energy cannot be recycled. We've already said that. You can change its form, you can move it, but it can't be recycled because of that second law. So in the case of laws of dynamics, we're going to use red arrows here. And since it's ultimately coming from the sun through the producers, energy also flows through each link in the chain. But again, it's not recycled, because at each level, at each conversion point, some of that energy is lost as heat. So there's not going to be any recycling here. So when a plant captures the energy sun, it's going to use that energy to convert the carbon, hydrogen, and oxygen into that glucose. When a chickadee eats the caterpillar, not all of that energy is going to be recouped. Some of it's going to be lost through metabolic processes. So when you combine these two, the flow of matter and the flow of energy, you can see how the fates are different in these systems. Again, the matter is the black arrows and the energy is the red arrows. As long as this keeps going, the system will be just fine. And from our best estimates, there's probably about 5 billion years to go in the life of that particular star. Now, there's a whole lot that can happen on this planet before that happens. But as far as that star is concerned, the one we depend on for our energy source, about 5 billion years. Scientists figure that our medium G-class yellow star is about halfway through its life cycle, is what they think. So that's what runs the system. So as long as the sunlight stays there, okay, we're going to have these links in the food chain. So instead of now having a chain or a straight link let's give those consumers different names. So we've got the producers, the plants. The plants that are eating the producers, we call those primary consumers. They're herbivores. Okay? Consumers that eat other consumers are called secondary consumers. Third level consumers are tertiary consumers. Now you may have quaternary, quinternary, sexternary, but ultimately you're going to get to somebody who's typically not being preyed upon by another organism, but they still meet the same fate anyway. But the point is that because of the laws of thermodynamics, there is decreasing energy available the higher up the chain you go. And for that reason, sometimes we use the model of a pyramid to portray how energy works in living systems. So at the base, you're always going to have a lot more energy, and you're going to have less energy the higher up you go. And by extent, well, I'm getting ahead of myself here. So I've said energy is lost at each level, but I haven't said how much. Well, a lot. As much as 90% of the energy is lost at each level and at each conversion. You say, well, how can that work? Well, I'm being completely arbitrary here. So in our little series, we had the plant, we had the caterpillar, which is a larvae of a butterfly or moth. We had the little bird, and then we had the hawk. Now up here, we've got the sun shining in all its glory, but how much energy can the plant get from that sunlight in this process? I don't know specifically. It depends on the plant species and all the, let's just say arbitrarily, the plant can recoup 1,000 kilocalories. All right. When the larva eats the plant, how many of those calories is it going to get? It's not going to get 1,000. It's going to get 10% of those calories. So it's only going to get 100 kilocalories. The bird is only going to get 10, and the hawk is only going to get 1. Because there's a 90% loss of the energy due to the second law there. This is why you'll always find fewer consumers than you have producers, and you will find that the higher up on the food chain you are, the more you have to consume. Right? Does that make sense? Okay. So again, the higher up this pyramid you go, the fewer number of individuals you're going to have. You can't have your top carnivores outnumbering these guys. It won't work. It won't work. The system's going to keep itself in check. Now, we said all this about heat being a useless form of energy, but that's only in terms of metabolism, acquiring it as a source of food energy. Living things still rely on heat. They have to have a certain amount of ambient temperature just to be alive. But considering most of the organisms on this planet are ectothermic, the term we use is cold-blooded, literally means they rely on the environment to regulate their body temperature. Mammals are endotherms, warm-blooded, and birds are endotherms, warm-blooded. And that's about it. There are a few exceptions, metabolically speaking, throughout the animal kingdom. But generally, all these guys are going to depend on the sun in some way to warm up their bodies to become active. And things like butterflies, their wings can actually act like solar collectors and warm the reason you see the word thorax flashing down there is the thorax is the segment of the insect's body where most of the muscles of movement are attached. Both the legs and the wings are attached to the thorax. So by warming up the muscles in that thorax, they are then able to become quite active and move and fly based on the amount of solar energy available to them. So they can't eat the heat, but they can use the heat. All right, let's switch over to human civilization now, because we don't often think about this. That in fact, most of the energy that we use on this planet to drive civilization, just like living systems, it comes from the sun. That's the ultimate source there. Fossil fuels are a perfect example of that. We hear that term thrown around a lot, fossil fuels, and it's in the context of coal and petroleum and natural gas. So what does that mean to say something is a fossil fuel? Well, it means that something about that fuel that we're using is definitely organic and typically is associated with something that was once alive, possibly long, long ago. In most cases, hundreds of millions of years. So things like plants, I've got a fern up there depicted. There was a time in the Earth's history where a lot of the fossil fuels that we use were actually formed. Now that's not to say all of them were formed during that time. A period around 300 million years ago, collectively known as the Carboniferous period. That literally means carbon-bearing period. Now, fossil fuels were formed before then and they are formed after then, but a lot of the ones we use, especially the coal deposits, were formed during the Carboniferous. And the reason is the climate of the Earth at that time, 300 million years ago, which was actually before the time of the dinosaurs, the land masses were in tropical latitudes. And so there was lots and lots of lush vegetation and probably acidic peat bogs all over the place. And so these plants would fall into these swamps when they died, but because of the acidic nature of the bogs, they didn't completely decompose. So some of that mass got preserved and compacted over time into peat and then ultimately into the different grades of coal that we see. We've got examples in the Naturalist Center that we show students. You know, you've got peat, then you get one of the first layers, first stages of coal called lignite, called lignite coal. And then you get another stage called bituminous coal. And you can ultimately get a stage called anthracite, which is very much purer and a little more difficult to come by. Most of what we use is lignite and bitumen when we burn energy today. But the point is, ultimately that was plant material that became fossilized, which hundreds of millions of years later is extracted and used for energy. So the coal that we burn today started out as plants up to 300 million years ago, which were deriving their energy from the sun just like they've always done. But that energy managed to be stored for that long period of time, and only now is the carbon dioxide and the oxygen being released back to the atmosphere when we burn it. Okay. So ultimately, that goes back to the sun. The same with petroleum. Petroleum is typically sometimes plant material, but in the right environment, but it's also microscopic marine organisms that die and don't fully decompose and formed kind of petroleum ooze in marine environments. And that gets processed and drawn out of the earth and made into the various petroleum products. And so that still, you're looking at animals, which were one time consumers, which were a part of the food chain, and still ultimately got their energy from the sun. The thing that I like to say about fossil fuels is, you know, obviously we depend upon them a great deal for our energy sources. And you can be as political as you want to about it, but there is one fundamental truth about fossil fuels, regardless of how you feel about the way we use them. They are going to run out. They are finite, okay? And we are consuming them at a rate faster than they have been restored in the earth. So I don't care how you feel about the issue, politically or otherwise, at some point, they're going to be gone. So if that alone is probably good enough reason to investigate alternative sources of energy, because you're just not going to have it indefinitely. Okay? Yes, when you burn fossil fuels, you're putting carbon dioxide and other things into the atmosphere. And we know that they have certain effects. But the only reason I say we better find other sources is we know they're not going to last forever. How long are they going to last? Depends on who you ask, you know. But regardless, that's why they are called fossil fuels. These things were once associated with living systems, but they ultimately go back to the sun. Now, there are some other sources that are from the sun that make perfect sense. I mean, it's obvious. Nowadays, we have these solar panels, which can directly collect solar radiation. Sometimes that's used for heat, to heat water. Sometimes those have what are called photovoltaic cells, which literally convert the sun's energy into electrical energy, which can then be stored in battery systems. But again, you're converting that energy. So just like a plant out there, you're not going to get 100% of what the sun's putting off. There's going to be some loss there in that conversion. You have to be in the right places around the world for wind farming to be cost effective. But there are such places, usually in certain ocean environments or in valleys, certain mountains where there's a constant or at least a frequent supply of wind to turn blades on a turbine and then produce energy, electricity that way. But this too is a form of solar energy. How so? Well, what is wind? Moving air. Well, why does the air move at all? Because the sun is constantly heating our atmosphere, but it doesn't do so at a constant rate around the whole earth at one time. So when air gets heated, what happens? It rises. And we're not going to just lose air. Other air is rushing in to take its place. Moving air, wind. Okay? That's still a form of solar energy in an indirect way. Now here's one for you. Hydroelectric power. Hydroelectric power. That can be traced back to the energy of the sun. How could you explain that? So first of all, the premise of a hydroelectric dam is to build an impoundment on a moving water system, typically a river, to get water, a store of water, potential energy, behind this dam, which can then be released at certain intervals to come across turbines to spin to produce electricity, converting potential energy into kinetic energy and further into electrical energy. So that's all convergent. How is that traced back to the sun? The water is back there. Think about the water cycle, something else you should have learned a long time ago. What is the water cycle?
With the evaporation.
Evaporation, condensation, and precipitation, right? Water's taken up in the atmosphere, condenses, falls back down. All right. So the only reason we have these sources of liquid water available is directly due to the solar aspects of the water cycle. Evaporation and gravity are driving those processes. Evaporation, gravity, precipitation, right? So it's still traceable back to the sun. Now I had somebody ask me, and it's a very good question, one of my students, what about, a lot of days, today we use nuclear power, have the nuclear power plants. And I thought, okay, that's good. There's probably not a direct connection to the sun there, but how could I make that connection? When we say nuclear power, what exactly does that mean? What are we doing to acquire power from a nuclear reactor? How does that process work? We've all watched The Simpsons once or twice, right? We've seen Homer drive home with the nuclear spent fuel going down the back of his pants, right? And that may be all we know about nuclear power, right? Except he wouldn't have survived that incident more than once,
Mr. Duke Energy?
He's doing a good job.
Well, the process that we acquire nuclear energy from is a process known as fission. Fission literally means to, if something is fist, it is broken apart. So basically, we have, and this is scary to think about, we have learned how to control nuclear chain reactions. Now, we know what an uncontrolled nuclear chain reaction is. It's called an atomic bomb, right? But in a certain environment, in a housing chamber, we have learned that you can fire at a super speed a neutron of an atom and hit a uranium atom, which is very, very complex. When you do it, again, law of conservation of matter, it's going to break into component elements, but the amount's going to stay the same. The amount of matter is going to stay the same in there. But the thing is, you don't just have one nuclear or one uranium atom in there, you got a lot in those fuel cells. And when that breaks apart and things go flying, it hits other uranium atoms and they break apart and go flying, and it exponentially increases. And every time you break that very complex element apart, it releases a lot of energy, a lot of thermal energy. We contain that. We use that heat to heat water. This is why you still find nuclear power plants around a constant source of water like a lake. They're heating that water, converting it to steam. The steam gets fired across the turbines. That spins a generator. That produces electricity. All right. So basically, we're using the same process of energy production that was first created when our solar system formed, because all of the planets have a certain amount of these elements in them, all right? And the uranium concentrated into certain areas around the Earth. The sun also has a thermonuclear process it uses to produce energy, but it's not fission. It's called fusion, which means putting things together. It's taking hydrogen atoms and turning them and forcing them together to form helium, and in that process, putting off incredible amounts of energy. So why don't we just do that instead? Why do we use fission instead of fusion to make our energy for civilization? Have you checked the last time to see how big the sun actually is? The reason we can't replicate fusion on this planet is that it would take an electromagnetic field right now a few thousand times bigger than the Earth itself to do it. Well, the sun's got that covered, right? So there's no problem there. So there's a little bit of a connection there with nuclear energy, but I can see where that might be a good exception. But there's definitely no doubt that because there is one place on Earth where the sun does not shine, and yet life thrives. These so-called hydrothermal vents in deep ocean environments. And so I've got a little short YouTube video that explains what this environment is, when and how it was discovered, and the fact that as far as we know, there's no solar energy involved. But instead of using photosynthesis, which is light, it uses a process called chemosynthesis, which is chemical energies, particularly it's sulfur coming out of these hydrothermal vents. So let me make sure I can get this to work again.
These scientists are headed 300 miles off the Galapagos Islands to a place known as 86 West. But the ultimate destination is 1.5 miles below the ocean waves. There on the seafloor is an unexpected oasis, fountains of warm water, and basking in it, bizarre animals. Biologist Tim Schenck from the Woods Hole Oceanographic Institution and geologist Steve Hammond from NOAA, the National Oceanic and Atmospheric Administration, are the chief scientists on this expedition.
To make sort of a crude map.
They are on a mission, backed by the National Science Foundation and NOAA, a mission to explore a mystery that began a generation ago. In February of 1977, National Geographic Explorer-in-Residence Bob Ballard and a team of scientists were sailing off the Galapagos Islands when they spotted them. Hydrothermal vents, and all around them, alien creatures the likes of which had never been seen.
We had thought prior to that discovery that all life was based upon the energy of the sun through the process of photosynthesis. that the sun was the life-giving power to Earth. Well, here was a system that was living independent of the sun. It was living in total darkness, not drawing its energy from the sun, but from the Earth itself through a process we now call chemosynthesis.
In chemosynthesis, bacteria absorb chemicals in the vent water to make organic carbon, or food.
The discovery of these ecosystems in the hydrothermal vents was very important because it told us that life can thrive, not just grow a little bit, but actually thrive in the absence of light.
This initial encounter with this new exotic world was not enough. Ballard and others would come back to the Galapagos again 2 years later in 1979. This time they found a vent neighborhood, more abundant than the first. They called it the Rose Garden. Scientists believe the only way to really understand these alien worlds is to visit them again and again.
Imagine if you just saw a winter time somewhere and you saw trees without leaves, right? And you came back a year later in wintertime and you saw trees without leaves, you would say, trees never have leaves, right? But if you come back in the spring and in the summer and in the fall, you'll see that these things become full of leaves, the leaves change and then they fall off, and there's a dynamic biological process that goes on, and it's that sense of understanding that we have yet to have at vents, understanding vent animals, and that's what we have to do.
Pretty amazing that we have that that environment where, you know, photosynthesis does not even occur. Any questions, comments, observations, or conclusions? Probably stuff you already knew, right? No questions? Thank you very much. I believe it'll be November. We'll actually get into a more basic study of ecology itself, talking about populations and communities, biological populations, biological communities. And some of this will come back into that discussion as well. But again, these should be things you're somewhat familiar with, and it's definitely things we talk to visitors about when they come here. So, thanks guys.
Thank you.